Dear students, today I am going to explain the important problems in semiconductors. The electron concentration in an N-type semiconductor is same as whole concentration in P-type semiconductor. An external electric field is applied across each of them. Compare the currents. Current I equal to NAEVD. Mobility of electrons mu equal to drift velocity by intensity of electric field. Therefore, drift velocity equal to mobility into intensity of electric field. Therefore, current I equal to NAE into mu into E. I electron by I N-type by I P-type. The current in N-type semiconductor by current in P-type semiconductor equal to mobility of electrons by mobility of holes. In N-type semiconductor, mobility mu E electrons. In P-type semiconductor, mobility of holes mu H. But mobility of electrons mu E is nearly 2 or 3 times more than that of holes. Mu E is greater than mu H. Therefore, IN is greater than I hole. So, electron concentration, the current in N-type semiconductor is more than that in P-type semiconductor. Second one, pure silicon at 500 Kelvin has equal number of electron and hole concentration. Electron and hole concentrations. Electron and hole concentrations, that is Ne equal to NH equal to Ni, intrinsic semiconductor, equal to 1.5 into 10 power 16 per meter cube. By doping indium whole concentration increases to 4.5 into 10 power 22 per meter cube. The doped semiconductor is. The doped semiconductor is. Relation between N intrinsic concentration of electrons in intrinsic semiconductor Ni square equal to Ne into Nh. Nh equal to whole concentration ఇచ్చారు. Electron concentration equal to Ni square by Nh. 1.5 into 1.5 into 10 power 32 by whole concentration 4.5 into 10 power 22. This is equal to 0.5 into 10 power 10 equal to 5 into 10 power 9 per meter cube. Here whole concentration Nh is greater than electron concentration Ne. Here Nh is greater than Ne and the doped semiconductor is p-type semiconductor. That is trivalent impurity. Indium is a trivalent impurity. The semiconductor is p-type semiconductor and concentration of electrons equal to 5 into 10 power 9 per meter cube. Currents in the circuit. Current in the circuit shown below is. Shown below is all diodes are ideal, hence R forward equal to 0 and R reverse equal to infinity. This is 5 ohm, this is 4 ohm, again this is 5 ohm, this is 2 ohm. These diodes are connected as shown 10 volts battery. This is plus, this is minus. Here this is 1, 2, 3 and 4. The diodes 1 and 3 are forward biased. And R forward equal to 0. Diodes 2 and 4 are reverse biased. R reverse equal to infinity. Therefore, the circuit can be rewritten as this is 5 ohm and this is 5 ohm. These two are connected to a battery of 10 volt. So resistance R dash equal to R parallel equal to R by N equal to 5 by 2 equal to 2.5 ohm. Current in the circuit I equal to V by R equal to 10 by 2.5 equal to 4 ampere. Next one. In the circuit shown below, the voltage appearing across the diode and load resistance will be of the form this is input voltage V input and T diode is in reverse bias. This is R load. Here diode is in, voltage will be dropped across the diode when the diode is in reverse bias. Voltage will be dropped across the diode when the diode is in reverse bias. In positive half cycle, diode is in reverse bias, and in negative half cycle, diode is in forward bias. Voltage dropped across RL. Here voltage is dropped across diode. For diode, the circuit waveform is, this is for diode, but voltage across load resistance is this for negative half cycle, and this for positive half cycle, diode and load resistance. Choose the correct circuit. Choose the correct circuit which can achieve the bridge balance. This is one Wheatstone's bridge. In this diode is in forward bias. This is galvanometer. Second circuit. The diode is in reverse bias. Here then this is galvanometer, 10 ohm, 10 ohm, 15 ohm, 5 ohm. Here 10 ohm, 10 ohm, 15 ohm, 5 ohm. All are equal resistances. 10 ohm, 10 ohm. This is 15 ohm, 5 ohm galvanometer. Again these are connected to same circuits. To balance the bridge, condition for balancing Wheatstone bridge is P by Q equal to R by S, 10 by 10 equal to 15 by S, therefore S equal to 15 ohms. To balance the bridge, resistance in fourth gap is 15 ohm. In case 1, if the diode is in forward bias, if R forward is taken as 10 ohms, bridge is in balancing condition. In the second and fourth cases, are not possible because reverse resistance cases R reverse is of the order of 10 power 5 or 4 ohms etc. Hence, bridge is not balanced. In case 3, for any value of RF, any value of RF, total resistance will never be 15 ohms. When any resistance is connected in parallel, the effective resistance will be less than 5 ohms. So for any value of forward resistance, the resistance in fourth graph must be less than 5. Hence, the bridge is not balanced. In first case only, the bridge is in the possibility to balance the bridge. In the given circuit, diode D is connected to an external resistance R equal to 100 ohm and EMF of battery 3.5 volt. Full stop. If barrier potential V barrier developed across the diode is 0.5 volt. Current in the circuit. Current in the circuit will be, here this is the diode D, resistance 100 ohm, a cell of EMF 3.5 volt is connected. Here VB equal to 0.5 volt. Current in forward bias, current I equal to E minus VB by R plus RF. This equal to 3.5 minus 0.5 by 100 plus 0 equal to 3 by 100 equal to 0.03 ampere equal to 30 into 10 power minus 3 ampere అంటే 30 milli ampere అవుతుంది. In half wave rectification, if the input frequency is 60 hertz, then the output frequency would be, in half wave rectifier, only positive half cycles are converted into pulsating DC. In half wave rectifier, output frequency equal to input frequency equal to 60 hertz. But in case of full wave rectifier, both the half cycles are converted into pulsating DC. Output frequency equal to 2 into input frequency equal to 120 hertz. The electrical conductivity of semiconductor increases when electromagnetic radiation of wavelength shorter than 2480 nanometer is incident on it. The forbidden gap of semiconductor is energy E equal to 12,400 electron volts by lambda in angstroms. This equal to 12,400 by 2480 nanometer means 24,800 angstroms in EV equal to by 2 and 0.5 electron volt. Energy gap of semiconductor is only 0.5 electron volts. In a PN junction diode, thickness of depletion layer is 2 microns. 2 into 10 power minus 6 meter, and barrier potential V barrier equal to 0.3 volt. The intensity of electric field at the junction is intensity of electric field E equal to V by D 0.3 by 2 into 10 power minus 6 into 10 power 6 by 2 3 into 10 power 5 by 2 equal to 1.5 into 10 power 5 volt per meter from N to P side. N to P side. The potential barrier in a PN junction diode is 150 milli electron volt. When an electron having energy having energy 450 milli electron volt travel from P to N side. P to N side. After crossing the junction, energy of electron is here. This is the PN junction. This is P region and this is N region. This is minus and this is plus. This side is negative and electric field is from N to P. Here an electron having energy 150 milli electron volt just crosses the junction from P side. Here energy, here this electron is repelled by this electron or this negative side and attracted by this positive polarity at n side. So the electron gains energy and enters the n region with more energy. So energy equal to E dash equal to 450 milli electron volt plus energy of barrier potential energy 150 milli electron volt. This is 600 milli electron volt is the energy of electron అవుతుంది. Energy of electron after crossing the junction equal to is 600 milli electron volts. మా దీంట్లో ఇంపార్టెంట్ మోడల్స్ ఇచ్చాను. అలాగే ఇంతకు ముందు పేపర్లో జీనర్ డయోడ్ పైన లాజిక్ గేట్స్ పైన కూడా ఆల్రెడీ ప్రాబ్లమ్స్ ఆర్ గివన్. సో ఎవరైనా ఛానల్ సబ్స్క్రైబ్ చేయకుంటే చేయండి, మీ ఫ్రెండ్స్కి షేర్ చేయండి, లైక్ చేయండి, డౌట్స్ ఉంటే కామెంట్ చేయండి. థ్యాంక్ యూ.